which is, so finally we're moving somewhere, and we're moving finally to deep neural networks. As you will see, deep means something more than just one logistic local linear model, so something more, and we call that deep neural network. So finally we're getting there, and we're in the area still of text classification. So what we did last time was we had this local linear model. So basically, where this is the input. So what was that again? What was X again in our model? I know it's too early for asking question. I'm sorry about it. Maybe in 10 minutes I'll ask again. So I'll if anybody doesn't want to answer, I'll answer it myself. So yeah, okay.
Vector or generated.
Yeah. So we call this also vector of features. Features. And you will see features in all machine learning. So a vector of features basically is this input vector to the function. All right, good. So then we have that thing. What was that? We call that, we gave it a special name. And it starts with W, so it shouldn't be surprising. And actually you had it in the exercise yesterday as well. So we had this linear function. Well, by the way, you actually implemented this thing. I mean, you might have implemented this thing yesterday, which is the a linear function, a linear node in a way, and then and the sigmoid on top of that. So how do we call this W? Yeah, weights. Yeah, these were the weights. Absolutely. Why are they weights? Why is it called a weight? What do you think? So what we're doing here, we're taking, this is a dot product, so we're taking each value from each feature, so to say, from the vector and multiply by the weight. So what we are doing, yeah, we're scaling we're weighting, so to say, each feature. So we're giving each feature importance. If the weight is 0, then the feature doesn't play in a role. You know what we might do, like the feature might have high weight, which gives us more to the overall sum. So this is why it's called weight. We're weighting the features, by the way. Okay, and then there's this tiny little thing called a B as a bias. Okay, nice. So we remember that. Okay, so this was the linear projection. So basically, this was taking features and projecting using these weights into some other space. Oh well, actually to a single dimensional space, to a scalar, basically. And then we squeeze it through this thing called sigmoid. So you should know sigmoid by now, because you have implemented that, and as well as its derivation. So this simple model, linear projection and then squeezing through the sigmoid, gives us a so-called local linear model, and it's for binary text classification. So the output of that is, okay, we have two other things, but what is the output of the sigmoid here? It has some natural interpretation. Do you remember what was that? So if we get this gives us a number in which range? Yeah, 0 and 1. So I'm starting from, yeah, in the range of 0 and 1. And what is the meaning of this value? It has a very natural interpretation, actually. So our network takes features, projects them into between 0 and 1. And the actual value between 0 and 1 is telling us something. Remember that? I mean, we want to classify, is it 0 or 1? So we want basically just two values, but we have the whole range in between, and it has a meaning.
Tendency to a Boolean answer.
It's a tendency to Boolean answer, that's correct. We have better words for tendency. Even better one. Confidence is also good. We have even better, even like something very straightforward. Between 0 and 1, yes. It's a probability. It's a probability of 1. Okay, so if this output 0.0.1, we have a probability of 0.0.1 that the output is true, which we say, okay, yeah, then it's more likely 0, okay, because it's closer to 0. So we make a cut in the half. Or not, we can decide it. Okay, cool. So that's what we have. And then we had this thing. Okay, so this is the gold label, right? I mean, we have the gray are constant inputs, and you implemented this as well. What was that thing here? What was that? What's the thing? I mean, we're trying to train this model. We have a gold label, we have the features, and we have the output of our local linear model, but we want to somehow make sure that this gets as close as possible to the gold label. So what we're measuring here? What is this? You in the back, yes. It's the loss function, exactly. So loss function. What is the loss function telling me? So it has some properties. The loss function outputs. So what is the output of loss function? Yeah. Say again.
How close we are to the goal?
How close are we? Yeah, I mean, this is how it works. It's saying like how close they are, but it's just the domain. Sorry, the codomain. What is the codomain of the loss function? It's outputting what? It's outputting a just number. It's just a real number, and we want it to be the real number. We want it to be mostly positive, so we don't want negative loss because, well, for some reasons. And also, as you said, it measures the difference between the prediction and the gold label. So we want to have a property that the closer these two things are, what's happening with the loss? Is it higher or smaller? The smaller it gets, exactly. So what is the minimum of the loss? Then 0, exactly. Okay, cool. Nice. So this is the loss, and as you might remember from previous or the second lecture, when we try to learn from data, so we have this input data and we have these labels, we want to make sure that what the function is predicting is as close as possible to the gold standard labels, okay? And we're doing that by changing the parameters. So that's what you did in the exercise yesterday. So basically you have two parameters. These are constant nodes, and you want to adjust them so you get lower loss, and you adjust them gradually. So we want to minimize this. So we're minimizing this loss function. Okay, any questions? Good. So how can we minimize this function? You have a bunch of training data. So you have the x and y's, and you want to minimize this function. How do we do that? I mean, we talked about it already in the second lecture from a mathematical perspective, but now we're taking a machine learning perspective, which is basically the same underlying mechanism in there. So how do we minimize a function? How do we in general minimize any function of these two variables, right? These are the two variables which are changing in our function. So how do we minimize this function? Any idea? You know it already. I mean, how do you minimize a function? We did it before. We look at the derivative, exactly. So what will be the derivative here with respect to what? Yeah, so we want to look into partial derivative of the function we're minimizing with respect to w. So here this is a vector, so at the end it will be to all of those, and then as well to the last parameter to b. Okay, yeah, exactly. What is this thing called? Oh, yes. It's a gradient, yes. It has a special symbol. Anybody remembers the symbol of gradient? Yes? The triangle, it has a name. Do you remember the name as well? It's a nabla. So, okay, this is the gradient. Okay, good. We have the gradient. What is the gradient telling us? What is the gradient telling us? We have a gradient of a function. What is it telling us? At a point. We are at a point and then we have the gradient. What is it telling us?
Where the function ascends to, and where we have to go to get to a lower point.
That's almost correct. So gradient is telling us the direction. So it's a vector. It's telling the direction of the steepest growth of the function. Or it's basically, if you're in 2D, it's saying like, okay, this direction is upwards, so you have to turn around and go downwards, basically. Yeah, but this is telling the direction of the steepest growth of the function. Okay, so if we want to minimize the function, we take the other direction and go downhill by some step. And we had it in lecture 2 with these minimizing single variable functions, multivariable functions. Remember the banana function? We covered it everything already. Now we're basically just shifting our view and saying, okay, these are the variables we are trying to, this is the space of the variables we're moving into, and we're optimizing this complicated function. But if you ignore just the rest and take, okay, this is constant, this is a constant, this is just multiplication, you have something like a banana function or something else. You don't care because you know how to minimize it. Okay? Sounds great. So how can we minimize this function? Well, we take a gradient. Good. And if you remember, we are taking a gradient or the derivative, basically the gradient, multiple times and taking steps unless we hit what? Well, we have some stopping conditions. So what it could be? First, second. Okay, you start. A minimum. Okay, how do you know it's a minimum? You don't see the function. You're just, you're basically blind in the mountains, and it's just telling you, okay, go here, just 2 steps. Okay, 2 steps. And then maybe 1.5 steps. So how do you know it's a minimum? Yeah, okay, exactly. So you set up stopping criteria, and you say, well, if I don't move that much, maybe then I'll call it a minimum. Okay. You have another idea? Yeah, if the gradient is 0, you basically cannot move because you don't know where to move, and then you're stuck. And that's an issue if you get 0 gradient. We could talk about it last week in the exercise. If you get 0 gradient, it's bad. So 0 gradient is really bad because you don't know where to go, so you cannot minimize anything, and then okay, you're stuck. Any idea in the back? Yeah, I mean, if the loss is 0, yeah, if the loss is 0, then what does it mean in the gradient? Yeah, okay, so you get 0 gradients anyway, I guess. Do you? Yeah, because you're multiplying basically. So you get, I have to double check that, but if your loss is 0, then you got it. You have a global, I guess, minimum in a way. But it shouldn't be the case in this model, because for the loss to be 0, this would have to output exactly 0 and 1, which is never the case because it's a sigmoid. So you would have to output like minus infinity and plus infinity, or plus infinity, which is impossible. But it's a fair point. It theoretically could be the case. Yeah, so you're right. I mean, basically you say, if I don't move that much, I stop. There's another criteria which you might take into account, and this is more like from the, let's say, cost perspective. So the costs, because you're iterating, you're taking steps again and again. So what could be the other stepping criteria in the back? Say again? Number of steps. Exactly. Number of times. So you say, okay, the whole thing will train for a month, and this is my budget for training a month on the cluster, and I take like 1 billion steps, but then I have to stop it because I'm running out of money or compute power. I mean, this is not the case for this simple model, but this is basically the case for training any large language model where you have, I don't know, like 1,000 GPUs. So imagine your OpenAI, you just acquired 1,000 GPUs from Microsoft, and they give you half a year for training your GPT-4 or Llama 3 or whatever they're doing, GPT-4. So yeah, you want to use all that up. I mean, you won't find a global minimum of your loss function, but you want to do it as long as possible. So, and then you stop. Okay, this is great. So we just invented, or you just invented, gradient descent. And we call it stochastic gradient descent because we do it more wisely. So what we have here is a bunch of training data. So this is the training examples. Okay. Training data. And the training data, so we have n examples. And each of the example is a vector x, I, and the gold label, and y, I. Okay, so this is a one example. So a vector of features and the label. We're saying that, okay, we're going to use the gradient descent. well, this is the stopping function we just talked about. So what we continue until some stopping criteria are not met. For instance, small updates or running out of time. But we're gonna take a single training example. So we're gonna sample from the training data, just maybe randomly, just one training example. And we're gonna compute the loss function and use this computation of the loss function to compute the gradient. So well, here I'm using the G hat for the gradient, could be nabla, but G is also fine. So I'm computing the gradient of the output parameterized by these parameters, and the gold label, well, this could be vector too, actually, doesn't matter, with respect to the parameters. So these could be the W's and the B, okay? And then I'm doing here, this magic operation is saying, okay, take the existing parameters and take the opposite direction, because the G is saying which direction, you know, this is the gradient, so this says where I have to go up, but I want to go down, so I take a minus vector. And what was that again? Do you remember this? We had a name for that. Because the gradient is just a vector, but we want to know how much actually from this vector should we go. Yes, it's a learning rate, exactly. Learning rate. A learning rate. Okay, so we have this learning rate. I think it's called eta, but it doesn't matter. Some Greek letter, learning rate, some small number, and it's a hyperparameter. So you choose that. You say, well, my learning rate will be 0.1 or 1. Did we have it yesterday in the exercise? I guess so. There was some learning rate as a parameter in one of those functions. Okay, so if you did it, so you know what it means. If you haven't done so, we'll find it. We basically implemented one step of this gradient descent. So, well, we want to optimize here. So let me just yeah, okay. So what do we want to optimize? Any questions to this algorithm? Everything, yes.
How do I prevent it from going into a state of hysteresis? For example, if I give it an input and train against an output, but that defines other parameters or maybe like inverse parameters of another training.
Oh.
Or do I keep it from just switching between the two and not doing anything?
So I'm not sure if I understand your question, but let me just rephrase. So you would say, I picked one example and update the parameters based on this one example. And I move somewhere in the space of the loss. I update the parameters, the W's and B. But if I have taken another example, I would have done it differently, because the other example is giving me some different sort of information, right? So how do I know I'm moving right in this parameter space? Is this what you're aiming to, or something else?
Say I have an input vector.
And
in my training set, there's this input vector and answer 1, so both level 1, and the same input vector and both level 2.
Oh, okay. So you're saying in your training data, you have a vector. Let's say x1 would be 1, 0, 1, -2, and your corresponding God label would be 1. And you're also saying, there's an example x2, which is its feature vector 0, 1, 0, 1, and -2, and then the label for that is 0. That's what you're saying?
In that notion, like even if it's not that extreme, I have the same problem.
So yeah, sure. Yes, okay. So you're saying if the features are close to each other, but you have different labels, what will happen? Yeah, so the idea is, that's a good point. So basically, if you have this example, like they are the same, and you have two different labels for them, so what could be that? What could be the text? The movie was great, right? I mean, it's a text. You change it into feature vector, back of words or something like that. And then you say in one example it's positive, and in one example it's negative. This is basically the edge case you're saying. So what does it mean? I mean, can we have this case? And if so, what does it mean? So does it happen? Can it happen?
Sure. So we could imagine we have noisy data, so like handwritten data, real-life data.
Exactly. Yeah. So it might happen we have noisy data, which means these labels are not reliable that much. We might have mistakes. Excuse me. We might have mistakes in the data. Somebody just annotated, like, you know, the poor students were annotating data and just fall asleep and say, oh, this is negative, this is negative, this is negative. And then you end up in, so it might happen. And one way is like the quality of the data. And of course, we have the assumption that the quality is perfect. So the assumption we've been talking so far, like accuracy, F1 score, all the measures, we're assuming that the gold standard is really pure gold. And it's cut in stone. But as we saw, well, not really, because somebody had to annotate the data, or they scrape it from the internet, and internet is noisy and stuff like that. So this is one issue with the labels. Your other questions was like, if this is a little bit different, so 0.1 and 0. So there's just tiny little difference, which means in the feature space, these are very close together, but still, if the labels are correct, yeah, sure. But we want to learn a classifier that makes a cut in between, exactly. So we want to be able to distinguish those. And the role of the classifier, or the learning algorithms, is to find a classifier that actually will be able to distinguish those two, even if they're very close to each other. If it's possible or not, it depends on the circumstances, on the classifier, on the data, how much, and where there's separable stuff like that. But we want to achieve that in theory. Okay? You have a question?
Maybe a comment.
Yeah.
So the classifiers we've seen, we could also interpret like as a probability distribution, and then we can model the distribution of the data. So if we have this sample and like 100 ones and 20 zeros, and then we train it for 100 steps that way, and then one step zero that way, I'm sure.
Okay, so you would basically adjust the training data. You would,
like if this training has a distribution of ones and zeros. Like in this case it's 1 to 1, not very interesting, but if it has 1,000 cases of ones and 500 cases of zeros.
for the same input.
For same or similar, or
Yeah, similar is a different thing, but it's
let's say same input.
okay.
That should be a case.
Well, you will learn something. You will learn that maybe you will learn that the model is uncertain for this task, depending on the model. I mean, but typically it's so. I guess this is not the case for NLP most of the time. Like in NLP, you really have distinct documents, and they are sparse. So this is not the issue you're running into. Maybe in some other cases you have like noisy data, noisy labels, like a lot of them, and then you might try different techniques. But I guess in like majority of NLP problems, this is not the issue. So we're not dealing with that. We're saying, yeah, okay, there's a gold label 0 or 1, and this is the feature vector, and they are somewhere maybe close to each other, but far from each other in the feature space. And you want to find the boundary between, typically, okay? All right, let's move on. The thing is, exactly, well, I mean, this somehow follows what you were referring to, is that the loss and the gradient is based here on just a single example, single training example. So, but if you remember, we want to minimize the corpus loss. So we want to minimize the loss of all training examples. So if we do it for one example, well, what happens with the others? So what should we maybe do is to iterate over all these examples, get a loss of all of them, the gradient from all of them, and maybe then take the average of the gradient and take the step. Make sense? So we would go through not just a single example, but the whole data set. And for each point, we would compute the loss and the gradient, but then afterwards, we would have a gradient for each example in our training data. And then we can take the average. But it's very memory it's ineffective because it consumes a lot of memory, because you have to save the gradient for each training data. So we're gonna do something else. Also, one other thing is that if you take one sample and update your parameters, well, you might have taken like a bad sample, some sort of outlier. And if you have an outlier and train on this outlier, what's going? Sorry, I need to fix that here. Training on an outlier, you're risking to move the parameters somewhere bad. So you have something which is not not a typical example, some sort of outlier, and then you update on this outlier and you move your parameters somewhere off the track. So you get inaccurate gradients. Basically, we're estimating the gradients based on the single example. So there is better ways. So can we do something in between those two, like taking the whole data set or taking a single example? Can we do something in between? Yes, in the back. Oh, batches. So you had machine learning before, batches. Okay. Okay, yeah, that makes sense. Sure. Anybody who haven't heard of batches but has a solution to that, what can you do?
Take like chunks, compute the gradient.
Oh yeah, okay. So you can take chunks. Okay.
And
That's yeah.
so I don't know the terminology here, but I take a number of these functions, computed gradients,
Yeah.
and then minimize those. So combine those gradients.
Yes,
again.
exactly. So basically, everybody kind of would invent the batch. We call it batch, like the chunk, and it's an extension which we call a mini-batch, basically a mini-batch stochastic gradient descent. So it's an extension of the algorithm before. So again, we have the training data here, we have the loss function and stuff like that. But now we don't take a single example, but we sample randomly m examples from the training data. And m could be anything between 1, where we come, if we have m1, we sample one example and we're back here, or to the whole data set, but we take something much smaller, and I'll tell you why later. But anyway, so we sample m examples right now, and then for each of these examples, we again compute the loss and compute the gradient. And here, then we want to take the average gradient of all these. We can take the average of either summing them up to first or just having a small updates 1 over m here from this gradient to the overall gradient. So this is 0. Then we take the first, I'll just go through for example. So the gradient is now 0. It's a 0 vector. We take the first example, compute the loss, and then compute the gradient of this example. But since we want to make an average of m examples, then we just multiply this 1 over m and adds to the gradient. And then we repeat for the next example. So what we are actually doing is we want to have the nabla is 1 over m, a sum of e into m and the mth gradient. So this is what we are doing here. We're taking the average gradient for each of these examples, but we're just summing them up to one vector. So accumulating basically a small gradient each time. And then we take, after this accumulation, we take again the step. So this is the only the only extension is that we have multiple samples now. And this gives us the advantages. Let me see. Do we have something? Okay. Yeah. So any questions to this stochastic mini-batch stochastic gradient descent? Do you understand the algorithmic part, or is it something which is not clear yet? I think this is something you should know, right? You should know what is a mini-batch stochastic gradient descent, and we will implement it. We kind of started implementing it already yesterday. We will implement it next week for a simple problem. So you should know. I believe there's no magic. Maybe like if you're not familiar with all these mathematical expressions, it might be kind of unclear. But the underlying assumption is fairly easy. You take n examples for each of them. You compute a gradient, and then you take an average gradient of those and decide where to go. Okay. So what are the limitations of this m? So how big the sample or the mini batch how big the mini-batch could be. So what is telling us, do we have any constraints on the mini-batch? So what is better? What is better for the estimation of the gradient? A smaller mini-batch or a larger mini-batch? We're taking the average, right? So we want to estimate the average gradient over the data set. So is it better to have small, a fewer samples or more samples to have a better estimate of an average, of a mean, or expectation, if you will? What gives you better estimation of a mean? Fewer examples or more examples? More, yeah, the more the better, because you're, it's basically statistics. The average estimation, the error in the average estimation decays with the number of examples. So you wanna have more in your batch. Okay, so you want the M be as large as possible. Actually, you want the M to be as big as your training data, because then you have like the best estimate of the gradient, because then you kind of saw all the training data and you make the average over all of them, and then you make the best guess where to go next. Why this could be an issue? Resource constraints. Okay, why?
You don't compute us, and the ones we have are finitely sized. So
yeah,
we have finite memory, finite time.
Exactly. Well, time is not an issue, memory is an issue. So you need to put these into your working memory, because for each of them you need to store, well, everything pretty much, right? You need to store the gradient, so you need to store the partial derivatives in your computational graph, and it grows with the size of the batch. So if you have, I don't know, hundreds of parameters, that's not an issue. If you have 2.7 billion parameters, as in like large language models, you have to, you have to sacrifice your batches. So typically, or your GPU has only 80 gigs. Well, only, if you have NVIDIA 800, you have maximum 80 gigs. And you'd be surprised how big or how small the batches could be actually with large models. So typically, I don't know, 16, 32 samples, 64 and other stuff. So this is what, with large language models, rule of thumb will fit in your memory before you crash your GPU. Okay, so a batch size is a parameter which you need to design to fit your needs, and it has implications, because the smaller it is, the worse estimation of the gradient you have. So it doesn't, well, the training is not guaranteed in most of the cases, but it might tend to end up with worse solution. Okay, any questions? Yes.
That be problematic if I have like outliers in my data, assuming like larger batches.
Yeah, if you have outliers in your data and you make an average out of them, then the outliers will be kind of averaged towards the mean. So this is what you want, exactly. This is preventing you. So higher values provide better estimates for the corpus-wide gradients. So better estimates means like robust to outliers. Yeah, because they're just single outlier, but the rest will be somewhere differently. So you kind of average it out. Does it answer your question?
I want to like correctly get the outliers, like a example, maybe like kind of get hidden under the.
Yeah, they will. Yes. Yeah, but it's a feature, so it's an outlier for a reason. You have, okay. So outliers in the data, it's a special thing. So how do you model them? How do you approach them? Is it an error in the measurement, or is it a real outlier, and stuff like that? So we weren't covered here, but outliers obviously have their place. Excuse me. Okay, another question. So the mini-batch, as I said, can vary from just one, which is the online stochastic gradient descent, to the whole data set. Well, the smaller values allow more updates and turn faster convergence. Yeah, this is like empirical observation. And there is one thing which basically makes this very, very, very nice, this algorithm very nice to train on modern GPUs. Line 6 or 7, so this whole thing can be parallelized, because you're running computation of the loss and computation of the gradient on each sample independently, right? These samples are IID. So these are IID, independently identically distributed data. So sample 1 is independent from sample 2, or example 1 is independent from example 2. So you can compute the loss for each of these examples independently. So you can run it in parallel. So you can take for example 1, let's say one thread and second thread for the other example and so on. So you can parallelize. If you're on GPU, you know, there's other stuff for parallelization, which goes more into the actual implementations, but it's easily parallelizable, which gives you a super advantage of training faster. And that's one of the reasons why deep learning on GPUs works so well in the last 10-15 years. You can parallelize lots of things. Okay, so yeah, we shouldn't have finished it last time. Okay, so I think it was wise to move it today. So now, well, okay. So what we can do? We have everything to train a log linear model. We have the model. We know how to represent features, so back of words. We know how to compute the gradients, and we know that the gradients are useful for this stochastic gradient descent, where we iteratively go and update the parameters. Okay. You build a single layer neural network already, or should have built, or we will build next week. Okay. Now, the point is that so far we had our growth label in 0 and 1. Okay, so we have binary problem, which is kind of a simplified thing of the real world. So what if we want to classify into distinct categorical classes? And categorical means there's no ordering. So for example, if I want to classify the language of a document into 6 languages, okay, so I have a collection of documents, maybe news, and I want to say each document is one of those languages. So English, French, German, Italian, Spanish, other. Okay, so how do I represent this? How do I represent the gold label? So before, for binary, we had 0 and 1. How do I represent 6 different categorical values? So for each class, you would have value between 0 and 1.
Like if the X output would be a dog or something, animals only the class of dog would be 1 and all others.
Okay, yeah, that's a, so does it have a name? Because we had similar name for this kind of representation. So you were saying we have all zeros, and if it's the true class or the class actually is represented as 1. We had a name for that. All zeros and there's only a single 1 in the vector. We had a name for that. It has something to do with electricity, I guess, or wires. Sorry, say again? Einheitsvektor. I don't think so. We call it, you remember? We call it one-hot encoding, one-hot vector. All zeros and one value was hot, so to say, was 1. Unit vector is something different. Yes, it's not a thing exactly. So sorry to. So we had it one-hot vector, and which means, do I have it here? Yes. So this is the answer. One-hot encoding of labels. So we say we have a vector of size of the number of categories. So in this case, we have a vector of size 6. And then for each of them, we somehow arbitrarily map each value to each dimension of the vector. So for example, we might say English is going to be on position 1, French is going to be 1 on position 2, German on position 3, and so on. And the dimensionality is the number of classes, which I just said. Okay, so it's it looks straightforward, might not be, but any questions? Okay, so if you have 2 classes, can you use this one-hot encoding? If you have binary, can you use this one-hot encoding as well? Yeah, exactly. You could, because if you have two classes, so if you only have English and other, you could say with this one-hot encoding that it will be this vector for English, and for other, it will be 0, 1. So you could use the same mechanism, but for binary task, well, actually we are kind of like over-representing the stuff, because we need for this binary task just saying, okay, English is going to be 1 and other is going to be 0, and then it's fine, because for binary task, you need just one bit to interpret, like to express binary task. For categorical classes, it's better to have this one-hot encoding. Okay, why is that so? Why is the one-hot encoding better than some other encoding, like encoding it as a, I don't know, as a bit numbers, like 1, 0, 1, 1, 1, 2, and so on? Okay, no, we won't go there. Okay, so maybe if you come up with this, yeah.
If I think about the step where I have probabilities there, having two really similar things next to each other breaks this encoding of like just binary numbers.
Yeah, I think you're on the way. So there is one feature of this one-hot encoding. We had it in the word representation as well. So this is one property. And so look at do you know Hamming distance? Have you heard of that? Hamming distance? What is Hamming distance? Somebody is nodding there. I guess Christina. Hamming distance. What is Hamming distance? Okay, never mind. Anybody remembers Hamming distance? Yes.
The number of ones in a string?
Almost. So yeah.
We want the bit flips we need to get from one string to another.
Exactly. It's how many bits are different between two strings. So here, for example, English and French, how many bits are different here? How many bits we need to flip to get from one to the other? How many bits do we have to flip? Yes, in the back. 2. Yeah, exactly. How many bits we need to flip to go from French to German? 2. From English to German. Also 2. Okay, yeah. Which means the distances between these two, each of these vectors are the same. And this is what we want. We want them to be, there is no meaning of distance in these categories. And this is great. Because remember, there is no ordering of these categories. We don't want to make any decisions about any ordering, like French is, smaller number, English is larger number, and stuff like that. We don't want to do that. We want to treat them equally. And by using this one-hot encoding, we do treat them equally, because they have the same distance to each other, and there's no preference of, there is no natural ordering of those things. We just do this arbitrary mapping to one of those vectors, but then the rest is somehow, they are evenly distributed in the space. Okay? Good. So, and we want to, okay, so the task here is that we want to, the task is we want to classify into distinct categories. So now we know how to express the labels. Okay, so the labels will be now a vector, one-hot vector, not a scalar anymore. And so now we know log linear model or logistic regression model, and how can we do a classification into these categories? So we can do like the simplest thing is we treat each of these language independently and just run a model. Basically, we want to predict 0, 1 for this model. So for each of that, we would have the parameters of the model. For example, parameters for French and the bias for French. Okay, we can do that, right? I mean, if you want to predict whether this is English or not, or French or not, you have your weights and bias, and you run your prediction, your binary classifier, and you get your prediction. Does it make sense? This is the easiest solution you can do, right? So, okay, so we run this classifier for each of those languages, and the classifier will get some numbers between 0 and 1 for all of them, then and so on. And then well, we don't care about the probability of having each of the labels, but we do care about which the label is that. You know, what is the language of the actual document, given these parameters and biases. So sorry, weights and biases. So if we have this this function, then we look into which of the languages, which of the parameters gave the maximum value of this. Okay, so argmax, what is argmax doing? Well, it's telling me which arguments of those. I mean, typically, if you have argmax, you have to say which arguments are you finding of maximum. It's telling us for which of those arguments the function gives the largest value, the maximum value. Okay, so max is this is interesting. So what is some? Okay, if we have vector, let's say 0, 1, and 4. What is the max of this vector? So let's this be x. What is max of x? 4. Yeah, and what is argmax of x? Yeah, if you're if 3 because third position. It's a third position. If you're, yeah, it's interesting. So I would say like 2 because I'm implicitly counting from 0 position as a computer science. But if you say 3 because it's a third element, you're right. So you know, depending on how if you're a MATLAB person or a Python person. Yeah. So argmax, I would say if we're indexing from 0 would be 2. Yeah. So this is the same thing. Like which of those gives the maximum value? Okay. So, okay, remember we had this for each language. And for each of them, we computed this linear projection. So we take the input, this is the same for each L, and then multiply by L and edit the bias. Well, we can take these vectors and rearrange them into columns of a matrix, capital W, and we get one expression. Let me just have a look if I have an example here. Not yet. Okay. So what we did here is that for English, we took a x. How was that? So we took a x, multiply by the weight of English plus, plus b sorry, this should be English, of English. Then for French, we took again the x vector multiplied by w's for French and b of French. So this is what we did here. For each of the languages, we multiplied 2 vectors together and added the bias. So you can do now is that you stack those vectors together in a matrix and you get the same result, because now you have, here you get a real number, here you get a real number. So if we say, okay, we take a vector x again and multiply by, now the columns will be of the vector of English, like that, then the vector of French, like that, and so on, and then have all these B English, B French, and so on. Then we'll get a vector of the outputs for each language, for each language, which is the same as before, but we just stuck everything into the matrix. Doesn't make sense? I hope I have an example but I want to fast forward. Maybe I do have it here. Yes, okay, I have it there. So I have a better example than just this scratching, but the idea is that you can stack them together. So what does it mean to let me just move this away. So we're projecting input vector to output vector, okay. And if you recall from, well, lecture 3 or maybe lecture 2, high-dimensional linear functions. So we have a function from some number of input dimension to some number of output dimensions. So how are we going to project this vector? We talk about it like this projection from 3D to 2D on the wall. So we multiply it by a matrix and maybe have some bias here. And it gives us a projection to the output space, right? So this is linear algebra. We have one input space, have a projection matrix, so project to some other space, and that's it. It's a linear projection. So it shouldn't be new to you, hopefully. If it is, have a look into the, I guess, lecture 1 or 2, or some linear algebra if you need. So what does it mean? All these, okay, what's important about multiplying a vector by a matrix? So everybody knows how to multiply a vector by a matrix. This is great. Is the matching of the dimensions. So the vector, as we saw in the second lecture, we use vectors as a row vector. Okay, so this is our x. So then the W matrix has to be what? Okay, so this is input. Then the W matrix has to have the same number of rows, right? Because we're multiplying row by column plus row by column plus row by column. So this the dimensions have to match. So this is W. And then the B, again, it's the output dimension. Because now this is projecting into the, B out. D out. And then if you want to add another vector, which is the bias here, it needs to match a dimension. Oh, okay. Why did I put it here? Let me just fast forward to double check. Okay. Yeah, predicted multiclass. Oh yeah, so we're predicting into an we have multiclass classifier. So what we're gonna do is to project our input vector into some output vector. So the input vector and the output vector. And now the output vector, because we modeled, if you remember, we modeled the gold label. The gold label was a one-hot, right? So we had the correct Y was something like 0, 0, 1, 0, 0, 0, 0. And this has dimensionality D out. And we want to take an input and output something like that, right? This is what we want to do. We want to get a one-hot vector from our classifier. Or we want to know which of those, so here's the argmax, we want to know which of those was the answer. So these two are similar. I mean, once you get some sort of one-hot encoding, you know which class you predicted, so you don't have to run the argmax. But basically, this is what you want to get out of it. And this is what we are getting from this projection. Okay, so what is y hat again? What was that? So it's the index of 1 in the one-hot, right? So if we take something from argmax, it's outputting the index of that. So if y hat is 3, then the document is in 0, 1, 2. Okay, it should be depending on the encoding. So if we have indexing 1, 2, 3, 4, 5, 6, then this would be German document. Okay. Any questions? Doesn't make sense what we're trying to do now. Like we're projecting from, previously we had input dimensions and we projected into one scalar because we're interested in whether this is 0 or 1. Now we have again input vector, but we're projecting into number of classes, vector or dimension, number of classes, and the output should be mostly zeros and just one hot. This is telling us, which class are we, which is the, which class are we predicting is the one in the vector of outputs. Okay. Right. I think it's time for a break. Oh, right now. Okay. Shall we make a break? 7 minutes? Empirically, like last time I said like 5 minutes, it didn't work. 10 minutes would be too long, so let's take a 7 minutes. Okay, so we start 9:22. So we're gonna talk about representations and what do we mean by that. So we have, so now we are in this multi-class classification. So again, this is what? X, what is X again? The input, it's a vector of features, it's the input. Okay, so it represents the input. Then we have those two things, which are the weight and bias, the parameters. Okay, and this is our output. Our output is a prediction. What is it? What is it mathematically? Output vector. It's a vector. Yeah, it's a vector. How big is this vector? Well, big in terms of how many items has the vector?
6, but it's size of the different labels.
Number of classes, exactly. Yes. Okay, good. So this is no, okay, we're on the same page. Good. So the vector X, so to say the feature vector, represents the document. So it's the input representation, and we spent quite some time last week to talk about how to get from words into a feature vector, right? We talk about like back of words, yeah. So back of words, what is this? What is the V? Anyone remembers? In back of words, what is this V? We use it for something. The vocabulary, exactly, the vocabulary. So we build the vocabulary. And so the input vector was super huge because we had vocabulary of hundreds of thousands, maybe, or tens of thousands. So this is one representation of the input. Well, okay, but in a way, the vector which comes out of this projection is also a document representation, but it's not, it's a specialized for this language prediction task. It represents the language of the document, right? It's a feature vector which represents the language of the document, because what we're getting out of here is a vector of 0, 0, 1, 0, 0, 0, for instance. So it does represent the document as well, but it represents something else than the original back of words. The back of words represent the distribution of words in the document. This represents a distribution of languages in the document. But it's also a representation of the document, isn't it? It's saying something about a document. You agree? Is it a good representation or not? Is this a good representation or not? As contrast to, let's say, back of words. Is it good or not?
Or representation and not to the content of what is in the text. So it is a good representation for our purpose, but not to represent the words.
Yeah, it depends. So the short answer, it depends. It's a good representation if you are interested in the language of the document. Yeah, then it's a great representation, because then you know exactly what languages are in the document. You don't know anything else. So maybe it, if you want to do the sentiment analysis on this representation, sentiment prediction, then it's useless because sentiment has nothing to do with language of the document which is written in. So, but it's super specialized for the language prediction task. But it's again a representation. Okay, so it's important to understand. Representation of document doesn't only mean the input features, it's also maybe some other projection. So we're projecting from one space to another space. Both of them represent the document in a different space. Okay, so these two spaces before projection, so the X, and after projection, are different spaces. They have different meanings. The first one is, okay, each dimension is a number of words. So we have 50,000 dimensions, and then we know where the document lives in this vector. The other one is much smaller, 6 dimensions, and it says, oh, what's the distribution, so to say, of languages in this document. So it's different space with very different kind of meanings and dimensions. But we can map from from one to another, and both are representing the document. So actually, we have this matrix W. So again, we have this formula. So input times the matrix. Now let's ignore the B completely. Let's have just a feature vector multiplied by this weight matrix. So then we have 2 views on this W, and one is if you look at this from the row perspective or from the column perspective, and I'll tell you why. So each of these 6 columns, so this is the W matrix, okay? The W matrix, it's important. This is the W matrix. Why is it W matrix? So what's the dimensionality of W matrix? What's its dimension? How many rows do we have in this matrix? Size of V vocabulary, yes. Times how many columns? Number of categories times I would say size of lengths languages. Okay, so we have 6. Okay, so this is number of, well, or this is basically the output dimension. Output dimension, this is the input dimension, right? So we have 50,000 here, and here is 6, because we're projecting from 50,000 space into a 6-dimensional space. So each of these 6 columns in this matrix, and we don't know where the matrix came from, let's just say now it's random or it's learned, each of those 6 columns corresponds to a language, is a size of the vocabulary dimensional vector representation of this language in terms of its characteristics, word unigram patterns. So if we learn something about, we have this column, this matrix, the weights here are telling us something about the language, right? Because we're projecting the words, the one-hot encoding through this matrix. So it's telling us each word, what's contributing to the language, each word of the vocabulary. Why is it so? Yeah, because we have here, the multiplication is just input vector. So we have the X. And multiply by matrix saying, well, let's multiply first by the first column. Okay, so it's going to be N. Oh, okay, so what is it saying? This is weights. And we had at the beginning, I asked what the weights mean. The weights mean like weighting each feature by some number. So it's the weight. Oh, we take the first entry here in this feature representation and multiply by the weight for the first entry in the representation. And it's telling us how much it contributes to the overall sum. Then we take the second entry, multiply by second entry in this column, and add it here. And so on. So it's basically weighting each word from vocabulary, from the input, by its weight for this task. So each of the columns represents something about the language. It says which language, available category. So this is the language. What the language has, well, there are words, and some words have different weights for this particular language. Okay. So these columns do represent something about the task and something about the language or about the categories. So we can maybe, if we have, let's say, similar columns, which could be English and German, these columns might be more close to each other than, for example, French and other. All right, so French and other would not be that similar, because you can then use this learner presentation to cluster languages. Basically, some languages which are close to each other in their distribution of words will be close to each other in this matrix, or their vectors will be close to each other. Does it make sense? So this is learning the representation of the language. if you take a column perspective. Okay, interesting. But however, we can look at the rows. So each of the rows corresponds to a particular unigram. So what was the unigram? What is a unigram? It's a very fancy word for unigram is a. We had bigrams. Do you remember bigram? So what is a unigram? It's a single word, exactly. It's a very fancy name for a single word. Okay, so each of the rows corresponds to a particular unigram or particular word from the vocabulary and provides a 6-dimensional vector representation of that unigram in terms of the languages it prompts. So here, the first row in the matrix is a representation of A, of the word A, but now it tells us some information how the word A is represented in different languages, right? We're projecting this into, yeah, so this is saying like, okay, you have each language has some weight here, and maybe this is how the word A is differently distributed in each of those languages. Okay, does it make sense? Because it will have different values for different languages, but maybe we'll have similar values for similar languages. Or what's okay, if we have A and maybe we have D here, do you think they will be somehow similar in this representation? So these two columns, one for letter A and one for letter D. What do you think about them? Can you reason about them? What the vectors will look like? Do you have any intuition? Sorry, in the back.
They're both English words, both not German words, so maybe like the weight for English is high, the weight for German is low and low.
Yeah, okay, right, exactly. Yeah, they will have similar, they might have a similar distribution of the words because they're both English words. Yeah, that's correct. Exactly. I thought more about like distribution of semantics, but we're not there yet. So sorry about it. It was a question to really ask, but you're right, exactly. They will have a similar pattern of distribution because they're English words. So they're most likely to occur in English texts and not in the others. Yeah. Maybe zoo will be different. Okay, that's interesting. Maybe zoo will be completely different because it might have, you know, a different pattern because it occurs in all languages in this task. Yeah. So again, it gives us a dense representation of the input features. So let me see whether this is really important or not. Maybe we can skip that. Maybe not, because it's just mathematics. Oh no, it's important. Okay, sorry, but it should be easy. Okay, so we have this average back of words. Oh, okay, what was that again? Back of words. So we have a document D, and D with its index I is a word in document at position I. And the output is so this is one hot vector. Okay, so X with this indexing is a one hot vector of word I. So if we have the cat set, so this is D1, this is D2, and this is D3, right? And then if we have vocabulary A, the, B, cat, blah, 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 set, right? This is the vocabulary. Then the one hot vector of D1 would be 0, 0, 1, 2, 3, would be 0, 1, 0, 0, 0. For the cat would be what? What would be one hot vector for the cat here? If we have this vocabulary, if you can read it, I'm sorry, my handwriting is not really good. So the one hot vector for cat would be, we have cat at position 3 would be 0, 0, 1, 0, 0, and so on. Okay, so this is like one hot vector. And we took the average back of words, so we basically sum them up and divide by the number of words. We had it already. So back of words, last lecture, you should refresh if you forgot. Basically, it's saying for each word, I'm taking it's one-hot representation and just make an average of all of them in my document. Throw in the back and take the average kind of vector. So, okay. So this is the X. This is the representation of the input, the input features. Now we have the matrix, the projection matrix. Okay, so what we're gonna do. Okay, so this is basically plugging this equation here to X. So we're extending. We have the sum. So this is the one-hot encoding, and we're still multiplying by the matrix. Okay, all good. This is simple. Basically plugging into the equation, right? This is the projection, and we said X is the back of words, so we plug the formula for back of words here. So this is just standard algebra operation. Okay, so what we're gonna do next is, because of the properties of a sum, we're gonna put this into the sum. We can do that, right? I mean, how is it called? Distributivity of sum or multiplication and addition, right? You can do that, right? Why can you do that? Well, if you multiply the sum by something, you can plug it into the sum, multiply the terms. That makes sense? Okay, mathematics, good. So no surprise, we plug it here into the sum, and let's move on. So we ignore the bias here. Okay, and what happened here is, okay, so what happened here? We multiply this one-hot vector. So this is one-hot vector, remember? This is, oops, sorry. This is the one-hot vector, so it means it's all zeros, and there's one position which is 1. So what happens if we multiply a one-hot vector by a matrix? So what is it doing? Let's have a one-hot vector, for example, 0, 0, 1, 0, and multiply by a matrix of 2 columns, let's say 1, 2, 3, 4, 5, 6, 7, 8. What happens? What is the output? So first, yes. Just get the third row, exactly. Well, this is the output. It's going to be 5, 6. How do you get there? I mean, you can do like very naively the algorithm of multiplying matrices and vectors. So, okay, this one multiplied by, okay, 0 times 1 is 0, 0 times 3 is 0, 1 times 5 is 5, plus 0 is 5. Okay, so you can naively basically do this algorithm, but basically it is like putting a mask here saying, I have colors, let me see colors. Okay, so saying only that one will be selected and all of them will be ignored. So it's basically masking selecting one row of the matrix. And this is what we have here. So this is because di is the word at a position I. So it's saying, well, okay, for this word, which was, I don't know, the cat set or whatever, we just take the eth row in the matrix. So we're basically taking a subset of the projection matrix. Okay, interesting. So why is it interesting? Yeah, because it's we can also take, let me come back. So sorry, just any question to what we did here? It's just some, yes.
Wouldn't it still be a 2 times 4 matrix?
Where?
Just,
this?
Yeah.
No. You know why? So what will be if you have a?
The number should be 0.
No. And why? It's no, and you have to know why. So why is it going to be like that? What is the dimensionality of this matrix? 1 row, and how many columns?
1.
How many columns does this matrix have? This is a matrix. This is a vector, but it's also a matrix. So how many columns does this matrix have? 1, 2, 3, 4. Do you agree? Okay, good. Then multiplying by a matrix. So what's the dimensionality of this matrix?
2, 6.
No.
2 times 4.
No. What is the dimensionality of this matrix? So we start with first Rows or columns?
So,
Okay, so how many rows does this matrix have?
okay, 4,
4. Okay, good. How many columns?
2.
Okay, 2. So, and linear algebra is saying that the output will be number of rows in the first term and the number of columns in the second term, which is going to be 1 times 2, which is this vector. Does it make sense? And if you think about it, why is it so? Is that we're projecting basically each of, well, okay, take some time, think about this projection, and you will understand why it works. We don't have time to go to that. It's linear algebra and projection of vectors by matrices. Okay, so it doesn't make sense. Okay, it makes sense now. Any other question? Good. So this was just simple manipulation of multiplications. Now we have another view. So this was the first view we had in the last right in the previous slide. And this was where we started with. Okay. Okay. So this is what we started with. Like remember, we had this. This is the 1-hot encoding times v. Let me come back. 1-hot encoding times v. So this is what we had before. Right. This is it. And we ended up also by another view, which is subselection of the representation matrix. Okay. That's interesting. So we call this as a, so we represent the document by selecting the words in the weight matrix and taking the average. Okay, so what does it mean? We have this W matrix, and we take for each word that appears in the input, we select the row, and from this we take the average. We average these vectors from this representation matrix. So that's why it's called also continuous back-of-word representation, because we have back-of-words, we throw them together, but the vector is a continuous vector. So it's not a binary anymore because it's in different space. It's not in the space of the vocabulary, which is this dimension, but it's in dimension of the output, which might be much smaller. So here in this case of the 6 languages we had before, this dimensionality would be 6, and we're projecting each word as a 6 size vector and take the average. And it still represents the document in a way. So it's continuous back-of-words representation. So we appear there by both things. I mean, these are the same, right? Either we sum up the representation vectors from this matrix, or we multiply, by summing word representation, summing up these word vectors first and then multiply by the weight matrix, or multiplying back-of-words vector by a matrix with each row corresponds to dense word representation. So the subsampling of the, not subsampling, like selecting the rows in the matrix. So these two are the same way. Does it make sense? Or not? Or you're asking like, why? Any questions? So you might be asking, why is it important? I would ask like, well, why do we care? That's my question. Well, we care because then now we know that we can represent words in not only as a 50,000 1-hot vector, but also some small dimensional dense vector, right? Why dense? Because in this matrix, these are not zeros and ones. These are just some numbers from the weight matrix. So this is the weight matrix. And these are some numbers, and we know that each word is basically in one row from this matrix. And it doesn't have dimension of 50,000 or 100,000 zeros and ones, but it has much smaller dimension. And it's also a representation. So if we have this W matrix, it gives us some representation of the word, as we saw before in these languages. And we can utilize that for having much better representation of words than just one-hot vectors. For example, in this language identification example, it represents each word as its distribution among these 6 languages. So that's why is it important. And we will see later on in one sub-area called word embeddings how exactly that works. So the matrix will be essential for representing words as a continuous back of words. So these representations, okay, we have this W matrix. So it's a parameters of the model, but this is also like learned representation, because when we train the model to predict the language, for instance, it learns something about the distribution of words among the languages. So it trains the weights such that we can, yes.
The word isn't precisely word anymore in this representation.
Say again.
A word isn't precisely a word anymore. So
yeah,
it's more a in the other example I can distinguish the
yes.
words exactly.
Yes.
In this I can't.
Exactly. Yeah, that's a fair point. Exactly. So if you have one-hot encoding, so one-hot encoding, you know that cat is 0001, 0000, and so on. And this will be of size of vocabulary. In continuous back of words, which really depends on this matrix. It really depends on that. So this is encoding in the matrix. You have a cat is 0.001, sorry, 112, minus 360, and so on. Yes. So which one is better?
Right now, before we have multiple words, they're essentially the same. They contain the same information. One has less memory need and is more compact, more dense. We could probably calculate stuff with it better.
Yeah. So the short answer is depends. It really depends on what you want to achieve, because one-hot encoding is something we designed as a representation. It's just one representation of words and one possible representation. It's discrete and sparse. It's a design choice. But why not have that in a vector which is a smaller dimension, but has maybe some other properties, maybe like carrying a meaning or similarities and stuff like that. We'll come to that later. But it really depends. A word is a word, but the representation really depends on what you want to achieve. And the good baseline is one-hot. I said, like, it's a very good baseline for text classification. It gets you very far, but there might be better representation. And it turns out that having a good learned representation as a continuous back of words gives you much better representational power of words later on. Okay. But I'm going too much in the future now. So any other question? So the representation are central to deep learning. So, and we want to learn good representation. So we want to learn such projections. So the representation here was a projection from one space to another space. And we want to learn them such that they have desired properties. And there's a question like, what is a desired property? Is it like, can I reason about them like having one exact word, or is it just a point in some space where I don't really know what these dimensions mean? This is also possible and quite common, to be honest, but it serves the purpose of solving the task. Okay. Wow. Okay. I think we'll manage. So log linear and multi-class classification, coming back. So yeah, there's one thing. So remember we have a model now which, okay, so what's the gold standard vector now for multi-class classification? What is it again? What was our gold standard? We said we're gonna use the one-hot encoding for gold standard, right? So 0, 0, 1, 0, 0. Yeah, okay, this is good. But now if you look at this, let me just come back here. This function, which is a projection from one space to another vector. So this is a linear projection and some bias. So this y hat is somehow could be any vector whatsoever, right? It could be anything. If you multiply input by some output, it could be in a range from minus infinity to plus infinity. So let me just come here. So our y hat, so this is the prediction, is something like yeah, minus 376 and plus 2022 and 0.01 and things like that. Yeah, so that's maybe not what we want, right? We want to make it much more revealing the gold standard label than some arbitrary numbers in unbounded range. Okay, how did we do that in the simple logistic regression model, in the log linear model, just with one class? We use some function. Oh, we use the sigmoid. Okay, good. So can we use a sigmoid here to get numbers between 0 and 1? We could. What happens if we use sigmoid here? What will be what will be the output here? So if we use sigmoid on each of those things, what will we get? A probability of each category. That's correct. We'll get a number between. So we might eventually have something like 0.001 and 0.99, 0.99, and stuff like that. Yeah, but this is not what we want, because this is not giving us like something like one hot, right? This is giving multiple ones. So you see the issue? It would basically be something like 0, something like 1, something like 1, and something like 0. So that's not gonna save us, because we want one hot.
I want something where I can round it to a state where I get one specific.
Exactly. I need to get here. I need to get here. So there is something better than just a sigmoid of all of those, because it won't save us. Do you have an answer or a question? We'll get to there. Okay. So now recap. We want to turn a vector into probabilities of classes. That's what we want. We want to have maybe probability of each class. And if you remember categorical probability distribution, so we have k categories, and we typically map them to natural numbers 1, 2, and k. So English will be 1, and so on. So each category, so probability of the variable being in category k is parameterized by this number. So this is just a recap. And the thing is that if we sum up all of them for all k's, right, for all categories, they must give us a valid probability distribution, so they have to sum up to 1. This is a probability distribution. If you have probability distribution over several classes, if you sum up the probabilities, you have to get 1. If you get more than 1, then something is wrong, either in the implementation or somewhere like fundamentally wrong. So it has to be 1 probability distribution, right? You distribute category 1, 20%, category 2, 20%, category 3, 60%. You sum up, you have 100%. Okay. Any questions? Categorical probability distribution? Good. So now the question is how we turn an unbounded vector in these k categories into a probability distribution. So what can we do with that? So we're having a numbers which are from minus, not infinity, minus a lot to plus a lot. And we want to turn it into, well, for each of category, right? And we have this vector, and each of them is this number. And we want to turn it into something where we have numbers between 0 and 1. And if you sum it up, you get 1. So what is some easiest solution to do so? How do you turn any numbers into something which is positive and sums up to 0 and 1? If you know the answer already, maybe let the others think about it.
The idea would be like a percentage of an average of the whole.
Oh, percentage of average. Okay, so this sounds good. So you would take, let's have three. Okay, let's have example of three values. So it would be maybe 1, 4, and 1. So how would you turn it into probability distribution? So you would say,
I would add them all up, which would be 6. So the first one would be 1 divided by 6. The second one would be 4 divided by 6, and the third one would be 1 divided by 6.
okay, good. We're getting somewhere. That's good. That's a.
Would run into issue with.
But it will break. So exactly. So this if we have -1 here, this will break. So how can we fix that?
Maybe using the sigmoid function first and then doing the.
Okay. You would say maybe sigmoid first, and then so running through all through of sigmoid and then normalizing.
Yeah.
That could work.
I don't know what the better.
Yeah, that could work actually. That could work. So you would basically turn each of them in between 0 and 1, and then you do the arithmetics. Yeah, okay, makes a lot of sense. I'm thinking whether this is the same we're going to end up with or not, because I haven't thought about it in this way. So let me just double check, or you will double check it. Okay, so I'll show you the formula later. You will double check whether you end up with the same solution or not if you use sigmoid for each of them and divide. Okay, so this will break. The minus will break, and if you have 0, this will break too. So this is not a good idea. You have proposed a better one with the sigmoid. So we have something which is called a softmax function. Maybe that's what you wanted to answer, right? Yeah, because you've seen it before. So this is basically I guess actually you can end up with the same thing. Let me think about it. So you take for each element, you first make it you want to make it a positive number, right? So you want to make it any number from negative to minus infinity plus infinity to turn into something which is bigger than 0, greater than 0. And then of course it has to sum up to 1. So you divide it by, you normalize it by the sum all of them. So it's rather simpler than taking sigmoid. You just say, oops, excuse me. You just say, okay, for each of them, I'm just gonna exponentiate it, and then I'll do the kind of normalization of that. So sigmoid will work, but I don't think it's the same solution. But I have to think about it. Okay, so it will guarantee us everything will be between 0 and 1, because this will give us a positive number, and then we multiply by the sum of these positive numbers to get a probability distribution. Okay, softmax. Any questions to softmax? Does it make sense what we're doing here? You could do something else. I mean, you don't have to exponentiate. You can take like a square, but it's not a monotonic function. So square would be, you have this u-ball, so it's not a good idea. So exponential function is like, you get projection basically to a non-decreasing function. Sorry, non-increasing function. Yes.
Now I get huge numbers. So
you get huge numbers. Yeah, okay.
Something I wouldn't really want.
So, okay, so here's the catch, right? Because if you have, so if x1 is 1, 2, 3, 4, 5, huge numbers, what is x of 1, 2, 3, 4, 5? It's going to be something super big. So you're running into computational issues. Which means if you implement softmax, like naively, like that, you're going to run into computational issues like overflow and underflow and stuff like that. So there's an implementation trick you can use, and we might do it in the exercises, how to implement it effectively to prevent overflow and underflow. Because you basically you're going to take the maximum of those. So here's a catch. If you ask ChatGPT, implement me softmax, it will give you the implementation with this kind of protection of the overflow. So I asked, should I reveal that? Maybe it'll really, well, no, it was the trickiest question in the exam I ever had. So I asked the students, okay, you ask ChatGPT, implement me softmax. And it spit out the output, which was correct. And then I ask, like, is it correct or not? Basically, what JetGPT says is something much similar to that, like a little bit of algebraic algebraic operations, and you end up with this exact formula. But it's very tricky to kind of do this exercise. Ask ChatGPT. Okay, so here's a homework. Here's a homework. Ask ChatGPT, give me implementation of Softmax. It will give you implementation of Softmax, which will look not like that. A little bit different. There will be some maximum something to prevent overflow. Okay, and then prove that this is the same thing. Okay, sounds fair? So it brings me to the idea, like, how can you trust ChatGPT without actually knowing everything, like knowing the stuff? If you ask ChatGPT to give me Softmax implementation and it will give you something else, then it's in every textbook. I mean, every textbook shows Softmax like that. It doesn't show the trig with underflow and overflow. ChatGPT gives you the trig with the underflow and overflow. So who knows? It's an open question now.
But it's something you can't expect ChatGPT to stay determinant for time. So if you have looked up, like, how does it implement this function, that might not stay the same.
Yeah, but the question is, like, if you're gonna rely on ChatGPT for programming and you're lazy to implement Softmax, or you don't know the trick, you say, ChatGPT, give me Softmax, and it'll give you Softmax, but it looks differently than what you know. It's true. Like this you can kind of prove gives you what you want. It gives you probability distribution. If you get more complicated function, you say, like, yeah, okay, I buy it or not. So how can you really, like, make quality assurance of the code that ChatGPT is giving you without actually knowing how to prove it by your own? Exactly. That's why I'm asking you, do the homework, ask ChatGPT to implement you Softmax, and then prove why is it correct. And I'm not going to put it into the exam because everybody failed on that. And I thought it's an easy exercise because you just multiply two exponential functions. Obviously, it's not. It's much harder because we're not used to it. So I'm saying, like, used to it and train it. People are saying, yeah, we should kind of, be reliable. Oh, sorry, we should really pay attention to ChatGPT output and verify it. Yeah, so go for it. Like, have you implement it and verify that it's correct. You have a question? Yeah, come on. I mean, no, it's a large language model. It's not trial improver. Okay, it's 3 expressions on one line, which you can prove it's correct. It's the same thing, right? But if you've never done it before, you're gonna say, it doesn't look like Softmax. So all students say, like, no, it's not. Many students say, like, no, it's wrong. Just few tried, like, oh, I know the formula for Softmax, by the way. Yeah, by the way, you should remember Softmax, okay? Remember Softmax. Like sigmoid and Softmax, you have to know. And some succeeded. So what I'm saying, like, try it on your own, okay? So coming back to your question, like, okay, overflow and underflow, these are implementation issues. Theoretically, this is the formula for Softmax. You can play around with that to make it more efficient, with fine precision on computer, okay? Well, okay, it was a detour, but I guess it's important. Okay, any other questions to Softmax? So, okay, this is how it computes the probability distribution. Yeah, okay, so now, okay, this is important because when we plug Softmax in our computational graph, we need to know not only how to compute the output, but how to get the partial derivatives with respect to each argument. So we need to do that. I don't have it here. You can do it as an exercise or just look it up. It's just chain rule. Chain rule derivations, and you get the derivatives for each of the arguments. And it should be easy because these are all exponents, so it should be fairly straightforward. Do I have the exercise here? No. Anyway, so you need to have the partial derivatives because you're gonna plug it into your network. This is pretty self-explaining. Okay. We have one thing here, and also this is that the Softmax, can we sort of smooth it with a parameter called temperature T. Why is it called temperature? I guess it comes from physics. So physics is using temperature because softmax has to do something with the state of the system and something, whatever. So, so like deep learning people adapted this temperature, and it has a reason, like the semantics come from other field, but it's basically saying you divide each value by this parameter temperature, and it's gonna smooth a little bit the softmax. How exactly? So here, let's have a vector 3, 0, and 1. And this is how it will look like if you put this through softmax, you get this result. So obviously the larger values will be the largest here, the largest probability, and the 0 and 1 will have like small probability. Okay, so this is what you get if you use the standard softmax. Now, if you divide it, or if you divide each term by a high temperature, like 100 here, it will smooth out. So all the probabilities will be more likely the same, right? So they're kind of, you're smoothing out all the probabilities. So if you sample from this distribution, the chances you're getting something, then the maximum will be larger. Or if you have a small temperature, basically you're spiking distribution to the largest value. So here we had some probabilities over 2 and 3, but the small temperatures, there's also almost no probabilities here. So this is important, maybe not for classification, but if we're going to use softmax for sampling from distribution, you might use this temperature for kind of a little bit adjusting the probability distribution here. So this is just a side note. Any question to the smoothing or temperature? Okay. All right, we still have some time. So what do we have? Recap. We have an input feature vector, and we want to output a one-hot vector because this is the category of we're classifying. We're classifying into multiple categories, so we want the network or the model to output a one-hot vector over a number of categories. What our model is actually producing now after softmax is not one-hot vector, but it's a probability distribution. It's outputting something between 0 and 1 for each category, and some have higher probabilities and some have lower probabilities. So now, if you remember how we train these things, how we measure the disagreement between the true value and the disagreement between the predictions, we had the loss, right? The loss we had for binary was what was the loss we were using for binary classification? We had one loss. It has a name. So okay, once again, last lecture and last exercise, we classifying a binary, so two categories, 0 and 1. We have the gold label is either 0 and 1, and we have the output is something which is something between 0 and 1. And we want to see how different they are. So we use this loss function, and we use one particle loss function, which we called, it had a name. It was a binary cross-entropy, exactly. It was cross-entropy, and we call it binary because it was just for binary values like 0 and 1. Okay, cross-entropy, cool. What is going to be now? So we had one gold and one prediction, but now we're, okay, excuse me. Somebody saw it before and know how to fix that. I would really appreciate any help. Now we have a vector. So the gold standard is now, let's say, three size vector, and the prediction is also, and it's probability distribution because it sums up to 1, right? I mean, let me see. Okay, gold standard. Oops. So gold standard is, let's say, 0, 1, 0. Is it the probability distribution? Yes, all are between 0 and 1, and it sums up to 1. So it's very spiky distribution with all the mass on one element, but it's probability distribution. Okay, so this is important. This is probability distribution. And then what's coming out of the network is something like 0.01 and 0.90. 0.08 and 0.01, right? So this is also a probability distribution. It's coming out of the softmax. Okay, so now we need a loss function for this softmax. We need to say how different these two things are in order to know how big the error is on this example. Okay, so we need a loss function. You haven't.
We can just do cross-entropy as before, but this time we don't say binary.
Okay, we use cross-entropy as before.
Because we still have probability distributions, so we can take log of the probability of left. We take the probability times the log of the predicted value, sum it up, negate it, and then.
Oh, okay. So you would basically take the binary cross-entropy loss, but now turn it into some cross-entropy loss.
Stop saying binary. Same
Cross-entropy loss. Okay. Any other ideas? I think that could work. I mean, that will work. Absolutely. Because nothing is preventing us from doing so. So we're going to use categorical cross-entropy loss, which is pretty much the same as the binary one. As we will see, the binary is just a simplification of this one. Okay. So also this categorical cross-entropy loss is also called negative log likelihood. Because of this log here, likelihood because of this probability over data and stuff like that. So if you see negative log likelihood, most likely it means this is a categorical cross-entropy loss. So again, we have a vector representing the gold standard distribution over the classes, right? So this is the gold standard here, 0, 1, 0. So this is it. And the output from softmax is again the y hat, indexed here up to k. And here, again, like the probability of the softmax, what does it mean? So this is a probability of being this category. So of category equals to position, what is it? Position 2. Okay, so this is probability, probability distribution that is a probability that the output is category 2. All right, and the cross-entropy loss is this beautiful formula. And it looks similar to the binary cross-entropy loss because we're taking a logarithm and multiply logarithm of this prediction, multiply by the gold standard, and then sum them up, and here's the negation. Okay, so I guess you can try to remember this one, or you can try to find a way how to get there if you know. So we have one slide here which might explain stuff. Okay, so cross-entropy loss, interesting. So if we have k of 2, let's do this. If we have k equals to 2, so we do for k1, we take minus I1 times logarithm of y hat 1, and then, okay, this will be the sum plus y2 times logarithm y hat 2. Oh, okay, which is minus y logarithm y and 1 minus, and now we represent, so in the binary case, the y2 is equals to 1 minus y1 because this is like the negation. So you end up here with y minus y1 times logarithm 1 minus y hat 1. And this is the binary cross entropy we had in the last lecture. Okay, so you don't have to remember this, but just if you see this and then you remember the binary cross entropy, this is the same thing roughly, but just represented differently. Okay, so you know that. So cross entropy loss. Any question how to compute it? Is it clear? I mean, basically it's a formula. So like if if you apply this formula, you will get cross-entropy loss if you don't, if you implement it properly. Okay, so any questions? Yes.
Entropy is complex. Same meaning as entropy physics, or is it something different? Because I only know the.
Here's the answer. So, entropy. It's been borrowed from probability distribution. So, entropy in physics has something to do with entropy in probability theory. Do you know entropy in probability theory? What is entropy in probability theory?
Really?
Not really. Entropy in probability theory is expectation of logarithm 1 over px, something like that. I mean, you have different notations, but it's expectation of this logarithm, and you compute it as a sum, which is x times px. Sorry, excuse me. Wrong. Logarithm p of x minus, because of the 1 over of the reciprocal logarithm. Okay, so there is a formula for computing entropy of probability distribution, and it's telling you something about how much surprising the random variable is. We don't go there this time. This is really like probabilities, probability theory class would be on entropy and its properties, but it has a meaning in there, and it has a meaning in physics about the unordering of probabilities in a space or something like that. I'm not a physics professor. I'm a professor of natural language processing, so I'm using this as a backbone in probability theory. Okay, if you know physics, there are some analogies, definitely. So the idea here is, and maybe okay, we can skip that. This is optional, but there's a reason. There's a reason why we end up with this cross entropy loss if we measure a distance between two distributions. So if you want to measure distance, well, not distance, like it's a divergence between two distributions. There is this KL divergence, also like a relative entropy. And if you want to measure the entropy between two distributions and do the little bit of math, you end up with the entropy of the gold standard, which you cannot move because it's a gold standard, and then what you can move is the entropy, is the cross entropy of the model, and that's why it's measuring a sort of a distance between two distributions. Okay, but we don't go there. It's just a background, so you know that it has a reason why it's in this way and why we use it for measuring. Basically, we want to measure distance between these two things, right? We want to measure how close they are. And in order to do so, we're just using the cross entropy. Okay, I guess we have 10 minutes to finish, or more, or less. You tell me. So 10 minutes? Are you still ready for deep learning? Or not? Okay, let me see. We have a couple of slides left. So linear models. Okay, we have linear models, and linear models can tackle problems that are linearly separable only. Okay, so here's an example. It's coming from the playground of TensorFlow, which is quite cool. So we have here data which are red points here and blue points here. And basically the feature vector is their coordinates here. So like this point, this example is represented as x1 and x2, which is in this case something like -3 and -3. Okay, so these are not words, these are just points on the 2D space. Okay, and they have the features are where they are positioned in the space. So this is how we represent the data here. It's a toy example, and we have two classes. We have red and blue, and they are in these two areas. And what we are trying to do in prediction is to find some sort of boundary between these two classes to say, okay, whatever is on this part of the boundary will be classified as red, and whatever is here will be classified as blue. Any questions to this? Does it make sense what we're representing here? Just points. Well, points are, I mean, if you think about one hot encoding of a sentence is also a point in the space, but it has more dimensions, like 50,000. Here we have just simplified to 2 dimensions for the sake of visualizations. So, and then, so we have the features like coordinates in one and coordinates the other x. And we have, so if you ignore all this, this is a linear function. So we have just a linear function. This is what we talk about. Linear function is actually making a line between these two classes and uses this line to distinguish, to the classification. Okay, so it's basically a line. That's why it's called also a linear function, because log linear means we would put some probability over these classes, but roughly it can only tackle things that are linearly separable. So what does it mean? Well, I have these two classes here, blue and red, and I can draw a line between those two. If I can draw a line, it's a solvable by linear classifier. Okay, does it make sense? Drawing a line between the feature vectors makes it solvable. So I can learn this model to distinguish between blue and red. Okay. If I have more complicated problem, for example, here, the blue points are here in this quadrant and here in this area, and the red points are here and here. Now, can I draw a line that will distinguish me these two classes? Can I find a line that will solve this task? Can somebody draw a line that will solve this task? Yeah. Good. Okay. Anyone else wants to try? One line that will solve this task. A line is a line, like not a curve. Okay? A line. No, of course not. I mean, you cannot draw a line anywhere here that will distinguish these two classes. You cannot separate them by a line, which means this task is not linearly separable, right? This is not, you cannot draw a line somewhere and to distinguish these two classes. There will be a lot of errors in here. You can only do you can reach some accuracy, but the problem by itself, it's not solvable by a linear line. Okay, this is bad. And I would say, let's take it home from here, because for the next 2 slides, I would need like 10 or 15 minutes. So we'll start next week from that. So recap for today. Oops. Recap. Okay, so we reviewed the binary classification as a linear function of words and sigmoid. Okay, this is from last time. And binary cross-entropy loss is from last time. We start with a mini-batch SGD. Okay, so we know now how to train a log linear model. We know how to do that. We use backpropagation for computing the gradient, and we use stochastic gradient descent to do the step in the parameter space. Okay. What we didn't talk about yet, we talk a lot about representations. So representations are central in this multiclass prediction. And we tackled a multiclass prediction where we said, okay, the target is not going to be a binary number between 0 and 1. It's going to be a vector of one hot. So our projection is not from a space to a scalar. It's a projection from a space to another space. And I'm going to represent this other space as a gold standard as a one-hot encoding. So the gold label, like a language, will be 001 and 000. And our model is predicting a probability distribution over these categories, which has some properties, has to sum up to 1 and stuff like that. And hopefully, the category with the highest probability will be that one which I'm trying to predict. And how can I measure the differences between these two vectors? We're using, again, cross-entropy loss. But this time it's not binary cross-entropy. This time it's just a generic cross-entropy. And the last point, okay, linear problems we had so far. Because so far we had just a vector multiplied by the matrix to some other space. A vector multiplied by a vector to a number. So if you remember linear algebra, matrix multiplication, it's a linear projection, it's a linear map, it's a linear function, which means it can tackle linear problems. If we have a nonlinear problem, like this sort of 4 squares, we cannot solve it with a linear classifier. We need to go somewhere else. What exactly is it going to be? That's something for the next lecture to start with. So I have bad news. So we didn't talk about deep learning today, actually, because the depth comes with stacking more stuff together next week. But I guess we are well prepared for actually tackling this problem next week. Any questions? All right. Have a great weekend.